Good morning, one and all. Myself, Dr. Srinivas Bachu, Associate Professor and HOD of ECE Department. The last session we discussed about variance, variance properties, skew, coefficient of skewness, then followed by some tutorials on those things we discussed. Clear? Yes or not? And the moments of a random variable about origin and about mean values we discussed. And the Chebyshev inequality also discussed. Now coming to this one, this moments statistical averages, mean square value, variance, like this, all the moments about origin and about mean values can be computed if we know the density function. If we know the density function. To generating this all moments, first moment about origin you want, one integration you have to do. Second moment another integration, third moment another integration, fourth moment another integration, like this multiple integrations you have to do for each and every moment about origin or about mean values. The time taking process. Now a single stroke solution, I am writing one equation, it's called moment generating function. I am writing one function, it's called moment generating function. It generates the moments. Like generalized manner, we are writing nth moment about origin. Only the nth moment about the origin. From this we can write out, we can find out any moment without solving this all integrations. That is called the moment generating function. We can compute the any moment about origin with the help of this moment generating function, it's MGF. To find out the various moments of a random variable, different integrals are to be solved. That is mean square value, third moment, so on, the variance, etc. Instead of solving these various integrals, moments of a random variable can be computed or obtained by solving only one integral named as MGF, moment generating function. This can be denoted as mx of t. This can be denoted as mx of t, moment generating function. This capital F indicates as moment generating function of the random variable capital X, suffix of x, of t. This t is not a time variable, it's a arbitrary constant or a variable. Clear? This is a mx of t. Sir, now what is my mx of t expansion? The moment generating function of a random variable capital X is defined as mx of t equal to, this moment generating function is nothing but as expectation, is one of the expectation. So this MGF will give the function in terms of the random variable x. So it is expectation of the e power tx, a random variation is there. That's why this is not a constant. Here random variation is there. That's why this is a not constant. My random variable is discrete or continuous. My random variable is a discrete or a continuous random variable. If the random variable is discrete random variable, then mx of t equal to summation. Why summation? I told clearly, this equal to can write expectation. I want the expectation formula in discrete case. Summation, whatever it is there, you note down as it is, t into x suffix I into corresponding assignment probability p of xi. This is the discrete random variables case. This is a discrete random variables case. The random variables are continuous, then MGF. Expectation is for continuous cases, integration, area enclosed by the intervals. That is minus infinity e power tx, you note down as it is, into density function with respect to x. This is a mx of t, moment generating function. Now we can generate the any moment from this, How to generate this? How to generate these moments? Now we will see. Continuation. I am expanding. Can you expand this e power x series, e power tx is there na, e power x series, e power x formula, power series formula, e power x equal to 1 plus x by 1 factorial or x to the power of 1 by 1 factorial plus x power 2 by x square by 2 factorial plus so on. This is infinite series form, power series form. Same thing here, instead of the x it is the t power tx is there, power is tx, 1 plus tx whole power 1 by 1 factorial, t square tx whole square by 2 factorial, tx whole cube by 3 factorial, tx whole power 4 by 4 factorial. Are able to follow? Now here t square x square t cube x cube t power 4 x power 4 like so on we are writing. Now apply expectation. Expectation is applicable to only the random variation. This is constant. Expectation of constant, expectation of k is always k, like this expectation of 1 is 1. Now t by 1 factorial, t is an arbitrary constant variable, okay na, it's not time variable, x is a random variation. This you can write out of the expectation operator, t power 1 by 1 factorial, expectation of x, t square by 2 factorial, expectation of x square, t cube by 3 factorial, expectation of x, so on. X is a real number range from the infinity to infinity and random variation. This expansion is a polynomial in t. This expansion is a polynomial in t whose coefficients are the moments. Now you see these coefficients are there na, moments, zeroth moment, here zero moment, here first moment about origin, second moment about origin, third moment, fourth moment, like nth moment about origin. Expectation of x power n is called nth moment about origin of the random variable x. From this moments about origin we can estimate the moments about mean values, central moments, like variance equal to mean square value minus mean value. Mean value and mean square value, these two are the moments about origin. Now I am getting the second moment about mean, central moment, variance can be obtained from the moments about origin. Clear na? Are able to follow? Right. Now thus MGF gives the moments of the random variable, but only moments about origin it gives directly. Indirectly some we can find out. M suffix 1, I want m suffix 1. Can you differentiate this equation with respect to t one time, that is d dash by dt power dash, okay na, d power 1 by dt power 1 of mx of t. Differentiate the mgf with respect to t, after that at t equal to 0 substitute, one time differentiation, t equal to 0. d by dt of this function with respect to t, differentiate d by dt of 1 0, d by dt of t by 1 factorial 1 by 1 factorial into expectation of x. With respect to t only I am differentiating, remaining are constants here. This expectation of x is always a constant, a real number. So now we will get here expectation of x. First one 0. Next thing is 2t by 2 factorial 2 cancel, t into expectation of x square plus 3t square plus 4t cube, like so on. From this term onwards, third term onwards, t terms are there, t terms are involved, but t equal to 0. After the t equal to 0 means these terms are vanishes, t terms are vanishes. Why means after that, after differentiation we are substituting t equal to 0. So only one term this will get, that is e of x, expectation of x. This is called the mean value. Mean value is m suffix 1. This is first moment about origin. Or you can write mean value of the random variable x, or you can mention as x bar, or you can mention as expectation of x, or you can mention expectation of x. This is a mean value. First moment about origin is called the moment about origin of the random variable x. Clear? This way we can find out nth moment about origin also. Nth moment about origin also. In generally, okay na? In generally we can find out, I am writing here, in generally nth moment about origin m suffix n equal to, we are differentiating the mgf function with respect to n times, with respect to n times of the function. After that at t equal to 0 we will get the nth moment about origin, nth moment about origin. This will get here, okay na? Like you see here 2t, 2 factorial 2 cancel, here 3t square, but here 3 factorial is there. Next time differentiation 3 into 2t, 3 to 6, 3 factorial 6 cancel. So it is a d to the power of n by dt t power n mx of t at t equal to 0. It is called nth moment about origin from the mgf function. If you want MGF, density is there. If you density knows, you can find out MGF. Once you got MGF, you can find out the n moment. Just differentiating will get. Now we'll see the properties. Then we will stop this lecture for this today's session. If x be a random variable with MGF is mx of t, then y equal to ax plus b is. So I want the MGF of ax plus b. MGF of the new random variable in terms of the x random variable. MGF of the ax plus b I want. Like we took the properties of the variance expectation, same manner we are taking here. My of t equal to expectation of y of t. Y means ax plus b. Expand this e to the power of axt, e to the power of bt. E power bt is constant out of the expectation operator. Expectation of e power ax into t. My of t equal to e power bt into mx of, right, y mx of. Now you see here e power axt there here. This we are writing here is equals to e to the power of bt into expectation of e to the power of at into x, like tx. Expectation of tx is called MGF, like expectation of e power at into x. This is not a t, it's at. So mx of t, but this is not a t, it's at. So we are writing mx of at. So this is constant, e power bt is constant out of the expectation operator. Hence, next second property, mx of t is the MGF, then y equal to kx. Then the MGF of y equal to kx is my of t equal to, same manner here ax plus b is there, here kx we took. What will get? Only this b means as this bt won't get, this term won't get, only mx of kt. Mx of kt. Yt, y equal to kx, e power kxt. So kt into x or x into kt. It is mx of kt. Hence proof. Next, y equal to x plus a by b. X plus a by b means as x by b plus a by b. Like same manner you have to expand, simplify, you will get the properties. Y equal to x plus a by b. Expand at by b, xt by b, and at by b is constant, e power at by b constant out of the expectation operator, and xt by means as here t by b into x, mx of t by b. This is a third property. This is a third property. Last one, if two random variables x and y having MGFs, mx and my of t's, such that mx of t equal to my of t, then x and y are said to be identical distributions, that is identical density. These are the properties of moment generating function. Here today we discussed MGF, and we are estimating the n moments. Nth moment about origin or any moment about origin can be estimated from the MGF. That's why this is called moments generating function, MGF. And we saw the properties. The next session we will discuss the characteristic function and tutorials on the MGF and characteristic function. Thank you.